Hello, we are Group 7 for the Senior Design 2 class of the 2020 semester. Our project is called Easy Herb. Our group members include Luna Vasquez, Lindsay Feldman, myself Chris Hernandez, and Kyle Patrick Magbu. In deciding what kind of project we wanted to work on, our research led us towards the topic of hydroponics. Hydroponics involves the method of growing plants without soil and using a nutrient-rich water solution. Further research showed us that the plants, specifically herbs, face multiple disadvantages when grown outside. This includes harmful insects and varied temperature. We wanted to create a hydroponic system that the user can place inside their home or apartment in order to target a population that is interested in growing herbs but don't have the outside space to do it. More research has shown us that other hydroponic systems on the market are either too large to be placed indoors or are too expensive for a typical person to buy. This led us in wanting to make sure that a hydroponic system is user-friendly and can let anyone learn the basics of hydroponics. Goals for Easy Herb include making sure that our system will only need minimum maintenance when it is turned on and that it is automated. Since the system will be kept indoors, ensuring that it is lightweight will let the user be able to move it around with ease. Easy Herb will have an easy-to-use interface that will let the user be able to see the system settings. Our last goal is to have our herbs grown in the best conditions while they're in the hydroponic system so that it maximizes their growth.
This slide shows the engineering specifications chart for our project. These specifications will be shown in our demonstration video in more detail to ensure that our system satisfies these specifications. Before we move on to the specific subsystems and individual components of our hydroponic system, here is a high-level design overview. This system will be made up of multiple subsystems and used to assist in the overall care of the plants. Within these subsystems will be the sensors necessary for system regulation. The system will include additional features such as the LCD and speakers to enhance the user experience. The picture on this slide shows an original vision of how the final product is expected to look.
The major components of our system were split into blocks. These blocks were then distributed among the group members using the respective color code. The chart on this slide has every major component listed with the group member's name and designated color, indicating that they are the primary person in charge of that component or subsystem. Later on in the presentation, we will highlight the secondary roles each person had while helping the person in charge of that specific component or system. The design of the enclosure is split into 3 areas. The top enclosure houses the PCB, LCD, and speakers. The grow lights will be hung from the bottom panel of the top enclosure. The herbs as well as the irrigation system are housed in the middle area. Also included are the temperature sensor, humidity sensor, soil sensor, and camera. The bottom enclosure holds a water reservoir with a pump and water level sensor and temperature sensor. The nutrients have their own respective reservoir and nutrient pump.
When growing plants hydroponically, supplemental nutrient solution is needed since the plants are not able to get the nutrients they need from soil. For this purpose, our project includes a subsystem dedicated to adding nutrient solution to the water. This system will determine how much nutrient solution is needed based on the amount of water in the reservoir, then dispense this amount from a separate compartment through a pump. There will also be a liquid level sensor that monitors how much nutrient solution is in the compartment, so the user can be alerted when this level gets too low. For the nutrient level sensor, it was decided to use a resistive liquid level sensor. The amount of nutrient solution needed is on the scale of tablespoons to gallons of water in the reservoir, so there will not be a lot of solution in the compartment at any time, and an accurate measurement will be needed. This type of sensor will easily fit into the small compartment and be able to accurately track the level of nutrient solution. To move the solution from the compartment to the reservoir, a pump will be needed. We decided to use a peristaltic pump since it will be more precise for dispensing the smaller amounts of solution that need to be moved. There's also no direct contact between the pump and the solution in a peristaltic pump, which could prevent possible issues that may arise if the solution were to clog a submerged pump. We decided to use this pump from Adafruit with a 12-volt power supply due to its availability. The pH value of the water being used can affect the ability of the plants to absorb the nutrients within it, so we will monitor the pH using a pH electrode sensor. When the value measured by the sensor is outside of a specified range, the user will be notified so that they may fix it and prevent possible future issues.
The watering system is a lifeline to the plants that are being grown, since this is the only way the plants will receive the nutrients they need. There are different types of watering techniques in hydroponics, but we decided on the drip irrigation method. This method will drip water slowly to the roots of the herbs from above. This will ensure that the water will directly hit the roots. The watering system will be housed in the bottom of the enclosure. It begins with the water pump being submerged in the water reservoir, and when the pump is turned on, the water will be pumped into the tubing system it is connected with. The water containing the solution will then be pushed through the tubing and will split into the different tubes leading to each herb. The water will pass through the herbs and will drip back down into a hole that will lead the water back into the reservoir. The water pump will be controlled by a relay. We will use a soil sensor to measure the moisture of the roots, and if the sensor deems it dry, it will turn the pump on and water the herb.
In order to minimize the need for user interaction, it is important that the water level within the reservoir is monitored. This will be done using an ultrasonic distance sensor, which will measure the distance to the surface of the water. This information can then determine the water level and the volume of water in the reservoir. When the level drops below a certain threshold, the user will be notified that the reservoir must be refilled. Besides alerting the user when needed, the data recorded regarding the water level will also be used by the nutrient system to determine the amount of nutrient solution that is needed when the reservoir is refilled.
The temperature of the water is important to monitor in the system to make sure that the water that is given to the herbs does not stunt their growth. If the water temperature is out of the optimal range, it can cause metabolic effects to the herbs. For this reason, we added a water temperature sensor to our system. The sensor will be submerged in the water reservoir and will record the temperature. The sensor we chose uses the DS18B20 digital thermometer and can measure a temperature range from negative 55 to 125 degrees Celsius with an accuracy of plus or minus 0.05 degrees. The cable length allows us to completely submerge the sensor with enough distance for safety. Almost all sensors use the DS18B20 thermometer, so the main reason to choose this sensor led to cost. The water pump is one of the most important components of the system, since it will provide the nutrients the herbs need to grow. When looking at water pumps, we need to keep in mind the GPH rating, head height, and power consumption. GPH rating is measured in gallons per hour and describes the flow rate of the water. We would not need a GPH rating of over 100 since our aim is to make our system as small as possible. The head height was also an important factor in picking a pump. The head height is the maximum height that the pump can raise water up. From the beginning of where the pump will be submerged to the vertical height the tubing will have, it won't be bigger than 2.5 feet. Power consumption was noted throughout choosing the water pump since we did not want to pick a water pump that will consume a vast amount of power. The pump that was chosen is manufactured by Mountain Arc since it has a flow rate we need and does not consume that much power and has a head height max that's more than enough for our system.
Since the water reservoir is a larger container, it was decided to use an ultrasonic distance sensor to monitor the water level. This sensor will be placed above the reservoir and will measure the distance to the surface of the water. This data will then be converted to the level and volume of the water in the reservoir. We choose to use an HCSR04 sensor from Adafruit since it is low cost and only requires a 5-volt DC power supply, so it can be powered directly from the microcontroller. To enable our project to be used anywhere, regardless of sunlight, artificial grow lights will be included. These lights will provide white light for the plants when it is needed and there is not sufficient sunlight. An LED strip will be used to provide the light, while a light sensor array will detect whether the plants are getting the light they need. This flowchart shows how the system will determine if there is enough light and what it will do based on its measurements. If the sensors measure insufficient light during a daytime hour, the lights will be turned on. If there is enough light or it is during a nighttime hour, the lights will stay off. For the grow lights themselves, we decided to use an LED strip since they are smaller and more energy efficient than other lighting options. Comparing different types of LED strips, we ultimately decided to use a WS2812B type. This type has individually addressable LEDs, so we could change the colors of each light if needed. It also only requires an input voltage of 5 volts, so it's able to be powered from the microcontroller directly.
The microcontroller is in charge of all the different subsystems within the device. Many different criteria were used to determine which microcontroller is best fit for our system without compromising important aspects. It was found that the Atmega 2560 has sufficient memory and enough I/O pins for our various components. Other options were either not powerful enough or were unnecessarily too powerful with an increased cost that went above budget.
Temperature and humidity can negatively affect plant growth if the plants aren't meant to withstand certain temperature and humidity levels present in the system. For this reason, a temperature and humidity sensor is needed to take accurate measurements to alert the user of any changes. The DHT22 model was chosen over the DHT11 because even though it is more expensive, it provides better accurate readings that can be the difference on whether the plant is growing in an optimum environment.
A moisture sensor probe is used to determine if the soil is receiving sufficient water from the pumps. This is useful to determine watering times of the plants. It is also useful if the water pump has malfunctioned and is no longer delivering the proper amount of water to the plants. The table on this slide shows the various moisture sensors considered, and the final component selected is the parallax sensor. This sensor has an operating range of 2 to 5 volts, which is within the range of other electronics we intend to use. This sensor offers a 1.5-inch detection depth, which will reach below the top layer of our chosen medium. Additionally, the hydroponic system will have a camera as another feature for the user. The camera will take one picture a day, which will be used to track the growth of the plants. Another feature we would like to implement is the camera will have a live feed which the user can access to see if the system is functioning as it should or if anything is causing potential harm to the plants. This is useful for when the user is away. The next component used in our system is a camera module. A camera is implemented into our system as a feature that enhances the user experience. The camera is used to capture the daily growth of the plant for the user to see, and additionally, this camera is intended to offer the user access to a live stream to check the status of the system at any time. The camera chosen for this system is the ArduCam 2-megapixel OV2640 Mini. This camera is chosen because it offers a color image, video capability, and can be controlled using SPI communication via the microcontroller. The camera chosen could easily be of higher quality, but it is used for proof of concept, and budget is a major constraint. So this camera was chosen as it met all of our needs and was within the budget.
Speakers were added to our system design to provide an extra incentive to the user. There is no benefit to the herbs, but the user will be able to listen to music while attending to them. The user will connect their phone to the speakers via Bluetooth and will be able to play music. An amplifier board is needed in order for the speakers to work, and upon looking at different ones, the X Station amplifier was chosen because it already has a Bluetooth capability implemented onto the board.
All sensor readings and device data will be displayed on a touchscreen LCD display. This display will be interactive so that the user is able to set up, manage, and change settings of the device without having to reprogram the microcontroller. To send data from the device to the online database, a Wi-Fi module was added to include wireless communication. The ESP8266 module was chosen for its availability and compatibility with the microcontroller. For testing purposes, the Node MCU model was used. However, only the transceiver will be included in the final build.
Here we have a brief overview of the system power consumption. Nearly half the power consumed in the system comes from the combination of the two pumps and the grow lights, while the remaining parts in the system take up approximately 14 watts. These calculations are done assuming that all components are running simultaneously, which is unlikely to occur. Using this worst-case assumption, an AC adapter with the appropriate power supply can be selected. Using the information from the previous slide, the best choice for an AC-DC adapter is one that will supply 30 watts of power, as using a 24-watt adapter would lead the system to potentially function improperly and fail. This adapter will allow for the entire system to run every part simultaneously, if that were ever necessary. Using an AC-DC adapter is useful for its versatility and can allow the system to be placed in any area with an outlet. The following circuit describes how the adapter will connect to the power circuits used on the PCB. The adapter can supply power directly to the pumps unregulated via the input DC barrel connector. From there, this voltage is regulated to 5 volts and 3.3 volts using an LDO circuit with additional protection diode in place. 5 volts will be used to supply power to the majority of the system, while the 3.3 volts is necessary for the ESP8266 Wi-Fi module. Additionally, relays will be used as digitally controlled power switches for the pumps, grow lights, and speakers. The relay module used in the system works using a 5-volt DC trigger voltage and allows the option of placing the connections in the normally closed position or the normally open position. Our lights and pumps will be wired using the normally open contact position, which will allow current flow when the relay is supplied power.
The microcontroller is programmed to take in data from the different sensors and control the pumps and lights within the system. The sensor readings are used to determine if the device will implement corrective action to make sure that the herbs are growing under acceptable conditions. These conditions are preset with default thresholds but can be modified by the user. This was done to increase the functionality and capability of the system. An additional feature of EasyHerb is the wireless communication. When a user is first setting up the device, they will be asked to connect to a local network and set up an account to link their device. Once set up, a user is able to take advantage of the remote access feature, making EasyHerb easier. A phone app for EasyHerb was created to enhance the accessibility to the device as well as user experience. The user can access the remote features on the app as well as display the current statistics of the device. The app runs on the EasyHerb web server backend. A user can access the same features remotely through a web browser if they do not have access to the app.
Next, we will discuss the PCB design. This is the schematic used to create the PCB, which consists of the MCU, power circuits, indication LEDs, the Wi-Fi module, and the pin headers necessary to connect all additional sensors and some peripheral circuits. The first iteration of the PCB layout can be seen on this slide. The PCB consists of 2 layers and is 90 mm by 90 mm. This PCB powers the system via the 12-volt AC-DC adapter. There are push buttons for reset and 4 mounting holes to hold the PCB in place. We have placed the order for the PCB and will solder and test it upon arrival.
Each sensor was tested individually for functionality and data was gathered when necessary. All sensors, pumps, lights, speakers, and the screen worked as needed. Relays were able to effectively connect the pumps with a 12-volt power, allowing them to easily be run when needed. There were concerns that the ultrasonic sensor would have difficulty detecting the surface of the water, so we had considered a bobber type design as a backup. But with testing, we were able to confirm that it does detect the surface of the water, so there will not be a need for a bobber. For prototyping the liquid level sensor, the sensor was submerged at different levels, and the resistivity value measured was recorded. From this, we were able to determine what measurement corresponded to what percentage level of the sensor being submerged. For the peristaltic pump, water was pumped between 2 cups in order to determine the flow rate. Averaging the results of multiple tests, the flow rate was determined to be 1.34 milliliters per second. This data will be necessary for programming how these sensors will communicate with other parts of the system.
This slide shows some of the initial testing that was completed for the light sensor and the moisture sensors. From these tests, we were able to find the threshold values that will be necessary in order to develop the code for the final system. In the test setup for the light sensors, a method of finding the average brightness in a given location was developed, which will help determine when the grow lights should turn on.
Throughout our project, we encountered some difficulties and challenges. One of them was the PCB. Our first PCB had some errors on it, and we had to make a second iteration of it. Luckily, we were able to get the second version to work. We were unable to get our PCB assembled by a company because of the pandemic, but through trial and errors, we were able to assemble it ourselves. Another challenge was when putting all the components together on the enclosure, we had to guarantee that all the wires connected to different pumps and sensors and were able to fit inside the pipes and make sure that the wires had enough slack. Another challenge was uploading full images to the server when dealing with the port forwarding security protocols set by team members' ISP, as this proved to be more difficult than anticipated. The following slides will go into detail about the administrative aspects of our project.
The budget projections for our project were broken down by the major components. These projections were used to allocate the appropriate funds for each subsystem.
The table on this slide shows our final budget for this project. Each major component is listed along with their price. Our total cost was $356.48, which is below our predicted budget we had at the beginning of our project.
The table on this slide shows the work distribution of our group on the major components of our project. The P's under the designated person's name indicate that they were the primary person in charge of the system or component. The S's on the chart indicate that the team member was a secondary person working on the specified system or component alongside the primary person.
This slide shows the percentage of progress that our team has made on the project. Our research is at 95%, while the design, prototyping, and testing aspects are at 100% done. By completing testing of all our different subsystems with the different sensors and pumps, we were able to guarantee that the overall system can support growing herbs. Our PCB is able to allocate the different systems on it. This leads our overall progress to come out to 95% done. Potential upgrades to improve the project include maximizing the total space in the enclosure to allow it to reduce its dimensions. Adding a third plant into the system will increase total herb production while upgrading the water system. Automating a system to balance the pH in the water reservoir would help simplify the user's need to help maintaining that system. And this now concludes our presentation. Thank you for watching.